In our last several videos, we took a look at what it meant for a function to be continuous. Now we're going to take a look at some further properties of continuous functions. Let's first start by taking a look at what it means for a function to be bounded. Right? So we've previously defined what it meant for a series or a set to be bounded. Now we're going to look specifically, what does it mean for a function to be bounded? So a function f with domain D and codomain, that's the real numbers, it is bounded if its range f of D is a bounded subset of the real numbers. Right? So we lean back on what it means for a set to be bounded. But that's the way we define how a function is bounded. If D is a compact subset of the real numbers and f is continuous, then the range f of D, that has to be compact, right? So if we start with a compact set for our domain, then the output of that function, the range, when our function is continuous, then the range of that function has to be compact as well. Our extreme value theorem is a corollary then to this. So if D is a compact subset of the real numbers, and if this is continuous, then because of the compactedness of its range, then that function has to assume both a minimum and a maximum value on this, on D. Right? So it assumes a minimum and a maximum value. Perfect. This next lemma is if we have this function that has a domain that's coming from the closed interval from a to b, if that function is continuous and it satisfies f of a is less than 0 and f of b is more than 0, then there has to be some point in this open interval from a to b such that the output of the function at c is equal to 0, such that f of c is equal to 0. It will take some time. We're going to walk through a proof of this. All right, so let's let S be equal to the set of all x values in the closed interval from a to b, such that the function value f evaluated at x is less than or equal to 0. We might note or observe that a is an element of this set, right? So we are assuming that f of a is less than 0. So a is an element of this set. So our set is not the empty set. It contains something. Right? S is bounded. This set is bounded above. It's bounded above by B. So what do we know about bounded sets? Well, if it's bounded above, then there is a supremum. All right, so this sup exists, and it exists as a real number. In that closed interval from a to b. So here's what we're going to claim. We claim that whatever that supremum is, that choice of C there, that when we evaluate this function at that supremum of this set that we've defined, that output is 0. So we're making that claim. The way we're going to do that is we're going to roll through. We're going to suppose that it's less than 0, and then we'll roll through and suppose that it's more than 0. and show that neither of those are possible to be the case, right? So suppose that f of c is smaller than 0. If it's smaller than 0, then there exists a neighborhood u of c such that f of x is less than 0 for all x in the closed interval from a to b intersected with this neighborhood u. So we're looking, so there is this neighborhood of u such that the function values, this neighborhood of c, such that the function values are in that neighborhood are less than 0 for every choice of x in the closed interval from a to b intersected with that value of u. Notice, so note that this choice of c is not equal to b in this setting, since f of c is less than 0 and f of b is more than 0. Thus, u contains this neighborhood about c. It contains a point P It contains this point P such that C is less than P is less than B. But the function evaluated at P would be less than, less than 0, since P is an element of that neighborhood U. And so P would have to be an element of S, but this contradicts the fact that C is the supremum, so C is an upper bound. So that contradicts that C is an upper bound. So now let's suppose the other thing, right? So let's suppose that instead of f of c being less than 0, suppose that f of c is greater than 0. Then there exists this other neighborhood. There exists a neighborhood, again, we'll say u of c, such that this time all of those function values are positive for everything in that neighborhood. So we have this neighborhood. For all x in the closed interval from a to b intersected with u. Note that C is not 0. Sorry, not is not A. Note that C is not A since f of A is less than 0. The f of C is more than 0. So those two things can't possibly be the same value. Thus, that neighborhood U, it has to contain a point it contains a point P such that A is less than P is less than C. So there's this point between A and C. Since f of x is greater than 0, for all x in U, f of p has to be greater than 0. And we would also have and no points of S are in this closed interval from P to C. So this implies this will imply that this implies that P is an upper bound. Maybe that doesn't seem like a problem, except for what did we say about C? But C is the supremum, so of S. So C is the least upper bound. And P is an upper bound less than C. This is a contradiction. Therefore, or thus, f of C has to be equal to 0. Can't be bigger than 0, can't be less than 0, so it has to be equal to 0. So we have this value in the interval that is equal to 0. All right, next time we'll take a look at the intermediate value theorem. We'll talk to you guys later.